All right. So with all this hype, everyone's kind of talking about WASM as being the next big thing, the next wave of cloud deployments. That was article after article when I was researching this. So many people were really kind of leaning into the belief that this is definitely going to be the answer to a lot of problems. And it's all reasonable. There's a lot of practical benefits, the growing language support, and there's a concerted effort for standardization which will help propel it. And it really does fit nicely with the kind of previous waves that have come before. VMs, containers, and WASM is going to be there to kind of work within that framework, that those kind of different compute types, and really enhance it to provide more efficiency there. But we're not quite there yet. So I'm going to talk to you, you're going to hear a lot of experimental, beta, alpha in some of the next few slides, and that's just because it's still really immature technology, but it's really progressing really quickly, and it's super interesting. So just keep that in mind. All right, to be able to get to this next level of more efficient deployments, to move WebAssembly from that browser to the backend, we're going to need something called WASI, another abbreviation for everybody's CV. So WASI stands for WebAssembly System Interface. So everyone knows an interface is just a common protocol for achieving certain means, right? So WASI, the point of it is to really provide a specific interface standardization for accessing OS level dependencies or needs. So think I, as a WebAssembly process, want to access a file. I want to create a socket connection. All these things that require communicating and working with the OS and providing that dependency for your application. And the great thing about WASI is that it is being designed openly. Not one company is really owning these standards. It's a working group of both community as well as business-led groups. And a lot of really smart people, much smarter than me, are kind of working hard to come up with those really good standards to hopefully achieve most use cases that WebAssembly would be good to solve for. And they have a lot of vested interest too. A lot of like Fastly CTO is on one of the working groups, and they have they're doing a very large push for WebAssembly with their services. So we've got standardization, hopefully, in the process. So what languages are currently supported with the current standardizations? So the first and best supported languages that you can really utilize WASM for is our system compiled languages. So these are your lower level, very efficient, very performant languages. Rust has become kind of the go-to language of WebAssembly for choice. It was one of the first to provide support, and it also is nice because you don't have to actually deal with memory allocation and deallocation using its novel approach. So you don't have a lot of the pitfalls that have plagued the college kids learning C++. So it's a nice it's a nice new language that really is well supported. C and C++ are great. C was actually the first language that got ported over to WebAssembly. Offers great support, but both Rust and C++ are high learning curves. So it's not the easiest language to pick up for all your new devs. One language that is a bit easier to pick up, but still a little bit more low level, Golang, has provided some really good support using TinyGo. So it doesn't technically support it out of the box with the default compiler, but TinyGo is more of an edge compute type compiler that it allows you to create smaller binaries and out of the box supports WASM. All right, interpreted languages. This also surprised me when I was researching this. I kind of thought interpreted languages would be the worst for this, but actually there's an elegant solution with WASM. So essentially the idea is to take your interpreter and turn that into a WASM binary, and then you provide it all the scripts, and then it will run. So within that WebAssembly process, it's not trying to do the whole thing, compile the whole thing into WASM binary. It's just doing that interpreter, and that's it, which is a pretty elegant solution. And so because of that sort of more straightforward approach, it's got pretty good support across kind of your most popular interpreter languages. So Python has some experimental support with CPython, which is the most popular interpreter. But there is a project called WASI Python that provides really good, robust support for the WASI spec. So that's become very popular for all the WebAssembly integrating SaaS services. JavaScript and TypeScript, there's several different projects that are kind of competing for the best bet. Quick.js is kind of run by WASM Edge, and it is really great for edge compute. It is mostly Node.js compatible, and it is really tiny, so it is really useful, and it makes a very small WASM binary out the back. But it isn't the most performant. That's kind of one of the major knocks to it, is in comparison to like a traditional Node.js environment. One of the ones that is positioning itself to be the most performant is SpiderMonkey, which is a great name, and it's run by Mozilla. It's still in the beta experimental phase. They're maturing quickly. What Mozilla helped come up with this WebAssembly idea in a large part, or push it forward. So they are really positioning SpiderMonkey to be a great way to be turning JavaScript into a WASM compatible binary. And Ruby, surprisingly, has been probably the quickest to release support. They have an official WASM build released, and they offer really good support for most gems. So as long as the gems or the libraries that Ruby supports doesn't have any C in it, then it should theoretically work. And they're actually working towards getting that full support for all of those other libraries as well. So this also surprised me. The runtime compiled languages are actually probably the worst for WASM right now. And it's effectively because of how immature the WASI standard is, So because there's a lack of garbage collection, there's a lack of multi-threading, which these languages already have runtimes, right? So they have .NET uses CLR, Java, Kotlin, and a myriad of other languages use JVM. So their languages and their bytecode that the compilers are built to expect certain things at their runtime. So because there's a lack of support currently with the WASI standard, and therefore the WASM runtimes won't really be able to support it fully. There is beta support for Kotlin, and there is experimental support for .NET, but until the WASI standard matures a lot more, it's really going to be a non-productive production use. There is hope, though. GrailVM has said once garbage collection becomes solidified that they will look towards supporting it, which GrailVM, hopefully most people are familiar with, a really great JVM that already creates a native image binary for Java. So. Another cool thing that I learned when I was researching all this is languages built for WASM from the ground up. So not only is the community really trying to support existing languages that are really popular, they're coming up with languages that are really nice in and of themselves, and directly compiling to WASM out of the box. So one of the most popular ones is assembly scripts. Like the name sounds and the logo looks, it is meant to be like TypeScript. And if you looked at it, it would be exactly like TypeScript. The only difference is you don't need an interpreter, right? So instead of it requiring a JavaScript engine to run, it actually compiles directly down to WASM. So you get kind of that performance, but you get that low learning curve with the language, which is really nice. Again, the downside to this language and any newly created language is that library support is still immature, right? So you can do a lot of things with it, but it's still not going to be necessarily be able to do everything that you can do with out of the box with Node.js. And the other nice thing is that they try and integrate it with existing tool chains like that TypeScript uses. So npm is your starting point. You get all your comfort and feel goods from using npm with assembly script. And the next one is Grain. I really like the look of this language. It reminds me a lot of JavaScript, like just really simple JavaScript, but it has a lot of opinions like Rust. So one of the things that I love about Rust is everything's by default immutable. So you don't get those memory issues. It's not going to be as scary to use. If you change it, you just don't. You're not allowed to change it unless you really, really want to. So that's something that Grain also does. It uses the mute keyword or mut keyword or whatever to make it mutable. It also uses a lot of similar declarative approaches to pattern matching and stuff like that, but it looks way nicer, and you don't have the same memory management approach of ownership. So it also uses garbage collection as well as assembly script, and you can define what you want your garbage collection algorithms to be. with these, as well as with like TinyGo. So you can say how much or how little you want collected and how often. So really cool new languages that are being progressed really quickly because of WebAssembly. So that brings me to WebAssembly on the server. All right, so we've kind of talked through the standardizations, what's going to help bring us to bring WebAssembly from a standardization. We've talked about some of the language support that's out there right now and some of the limitations there. So how are the ways that we can currently get some of these binaries on our backend servers right now? So kind of one of the straightforward ways or approaches is to do it embedded. So it's kind of what I was talking about before, incorporating it into an existing project. You're able, if you're a big Node.js or Dino fan, it's going to provide really good support out of the box because Node.js and Dino really try to provide parity with browser APIs. So those already provide support, and then there's other projects run by WASMer. So WASMer is a WASM runtime that basically is providing a couple different approaches and ways for you to run your WASM binaries. So one of those being to embed it into your program. So you have WASMer packages that you can include. So I know they have pretty mature ones for Python and JavaScript and TypeScript, but they're working towards supporting many more languages. Standalone. So this would be the ultimate goal if you're running your own deployments, is to have this universal runtime at your disposal. Obviously, there's going to be a couple different ways you can do that, just like with containerization in Java, right? We can put Java in a container, so we can put a WASM runtime in a container, give it that WASM binary, and provide it any other necessary files if it's like an interpreted language. And that will allow us to kind of use the WASM runtime in our existing deployment pipelines. Most people are using Kubernetes or some kind of container orchestration, so that kind of fits well within that same framework. The next step after that, which would it'll help you truly benefit from the size, the decreased size in the binary, is integrating our orchestrators, our container orchestrators or schedulers, if you're using like Nomad, with the WASM runtime. So this is kind of a really cool way of doing it. Docker Desktop is kind of provided a lot of really good local development support that does that. So I'm going to show that later, where you can have Docker Desktop, you can run your WASM Docker image, and you can just define the specific runtime that you want, and it's going to use that runtime. So instead of an image being megabytes or gigabytes, you can bring it down to almost kilobytes of size in order to run. And so that way, instead of your scheduler trying to juggle this very large file, loading it and unloading it, it actually is a lot faster using using WASM. So that's kind of an ultimate goal, to really providing a lot of people access to WASM using the same tool chains that everybody's using today. And another thing that is happening, as you might guess, just like containerization birthed a lot of really great platforms like Kubernetes, that's another thing that's happening now, is people are trying to build WASM first platforms to deploy code to. So you can deploy these various services to your own AWS, to GCP, wherever you want, and provide it simple configurations, and it will do the rest, right? Which is really nice. And the last kind of way, which is sort of like standalone, but it's a lot less, it's all obfuscated from you, is serverless. So we've got a lot of serverless providers that are starting to package your functions as WebAssembly and running it on the edge. And this is because of how fast those startup times are, how much smaller the packages are that they have to move around. So Shopify, they're the ones that created a JavaScript WebAssembly engine, and they've started to use WebAssembly for part of their functions as a service. A lot of other functions and services are looking towards better and better support. Again, to just reduce their own costs and increase their startup times, or reduce their startup times. And then a lot of these platforms that are becoming available that you can locally deploy, you can naturally assume that they will also start offering a cloud version for serverless. So again, you're just either building your WASM binary or writing the code and letting the platform take care of the rest. All right. So I got a few demos to do to walk you through how that practically works. Before we jump to that, is there any questions that you guys have? Any questions on the chat? Yeah.
Just have one. You mentioned that obviously it's going to be really great to work alongside JavaScript. It's going to help where JavaScript alone might struggle through certain jobs.
Yeah.
Do you have an example of something like that where JavaScript might struggle through a certain job and WebAssembly can help with?
Yeah. Yeah, so like for instance for Figma, they use a lot of use up a lot for image processing and things like that. So a lot of stuff where you really want, your heavy algorithms or heavy, where you really need that native performance. Tackling those types of problems with WebAssembly is what is currently being used. Eventually, the goal is not for the browser, but for the backend, is for pretty much any workload to be viable within WebAssembly, and it being still faster and more resilient just because of how quick it is to run. And
would it be overkill to do it for not so heavy jobs, just to make even them marginally faster?
So for the browser side, there's a diminishing returns because of the effort involved, right? So that was the whole idea with WebAssembly is it's for the browser is that it's supposed to be a tool for enabling a better user experience, but as well as a good developer experience. But so a lot of things are just going to be very easy and much easier to do from a developer's perspective using JavaScript. But the goal long term for the backend would be I can write JavaScript, I can deploy it within a WASM binary and put it in the cloud, and it's going to be easy peasy, lemon squeezy as my daughter says. So, any other questions? Awesome. Cool. All right. Well, I'm going to jump into a few. So I'm basically going to run through a few of these ways to do WebAssembly on the back end that we just talked about. Let's see. All right. Someone pour one out to the demo guys, make sure everything goes well. All right, so the first one I'm going to talk about is that embedded approach. So basically providing a binary to a backend service and using some utility functions. These are very contrived solutions, examples, but gives you an idea of what you can do in terms of hooking things together and hopefully the ease, and also gives you an idea of the size of like Docker images and the file sizes. All right, so, it doesn't. All right, cool. So it might be a little hard and pixelated for our viewers in the bar to see, but I'll try and talk through it to make sure everybody has at least an idea. But please speak up if it doesn't make sense.
You just zoom in.
Zoom in a little bit more.
Couple of points.
Is that better? Can everybody see that?
Is that right?
Yep. All right. So. So here is the kind of the index. I used .mjs because I was really lazy to do imports here. So this is kind of our only file, and this is to simulate if you were to kind of create maybe a simple function within simple HTTP request handling. So all I'm doing here is I'm using this script that was provided by TinyGo. To a certain extent, I had to modify it just a little bit, but to make it work exactly the way I wanted it to. But you can essentially, using that, I can load a Go WASM. So I built a Go module. So this is a very simple module that basically exposes this function, a get really complicated computation. It's multiplication. So just an idea of how you might go about exporting and importing this from WASM. And if you're working on the browser, there's bidirectional support as well. Same thing with backend. So you can also basically give your Go module different JavaScript functions to run. So there's inner communication that is possible there. So it's pretty simple. I got WASM, my Go WASM binary, and it's going to run. So then let's look quickly at the Go module, just to get that idea. I don't know if people are familiar with Go, but there's a lot more to the language than just this. So all you have to do to export is this comment, which isn't really nice. I hate it when languages and things use comments for actual processes. But the goal is to eventually make it to where it will kind of support actual exporting that is native to the way that Go works, which is using capital letters. But as of right now, this particular approach uses the comment of export. So it exports it with that name, and that's it. So that's all that this very simple Go module is doing. So I've got this Docker file here. All right. So what this is doing is it's putting it all together. It's going to build my Go module here. It's targeting WASM. All right. So that way, it in the format that I want, creates that binary. And then what it's going to do is just copy all that good stuff into a node Alpine, so the popular small footprint image, and run it. So let's see if this will work for us today. All right. So I've also written this in a Docker Compose, and I'll make all this code available after today. So I'll just clean up add some more comments and stuff for you guys. But if you've got Docker for desktop, then you're going to be good to go. All right, so Docker Compose up. Oh, I'm in the wrong folder.
You writing that without having to go to the website to work out what all the arguments are.
Hey, I did that right before here, so don't give me too much credit, Okay, cool. So, embedded Node.js, it's started, it's listening, wonderful. So now, if the one thing I hate about Docker, I usually just use WSL, but Docker for desktop don't really let you have access to the WSL instance actually anymore. So, curl localhost 8081. And there we go. Well, let's look at Docker for desktop and make sure that it's still running. All right, so we're running here. We've got 8081. Oh. I think I've got something there. Too many WSL instances up. All right. All right, let's double check. Good. 8082 now. There we go. Complicated calculation 6. Woo! That was fast. Super fast, right? That's all WASM. That's all WASM right there. That's what all the speed is. No, it's I'm just gonna look at the image size here, give you guys an idea of the bare minimum, right, of what this is kind of adding to the pod. So let's see, Docker images. We'll do a grep, and let's see. Don't want to show all the images, just want to show this one. All right, 53.9 megabytes. So that's pretty dang close to what it is out of the box with Node Alpine. I think it's almost exactly 53. So we're not adding too much here. That WASM binary is not too big. But yeah, there you go. That's one way that you can leverage WASM today, and that's pretty well supported with Node.js. And so if you've got really cool Rust, like especially if you're working with Rust or Go. Or C++, and you really like whatever services or algorithms are running in there, then you can port those over, use those, and it will provide really good performance for your backend project. All right, so let's go to the next one, and let's kill this. So the next one is about kind of the idea of how we run Java, right? I'm going to embed a runtime inside of a container. All right, then we're going to look at how big that image is and kind of what it does. Again, another very contrived solution, but we'll show you an idea. Any questions before I jump to the next one on that one? Cool. All right, so. All right, so for the JavaScript here, the nice thing about this JavaScript file is hopefully very, very familiar, very simple. It's just a JavaScript file. You know, this is what you would throw to Node or anything to run and create a very, very simple server that delivers a request on any route, right? So the real interesting stuff is inside of here. Oh, I hope the internet connection is good because I don't have any internet. This is not gonna. We're gonna see if I might have to hop on the internet somewhere here. There we go. Cool. Connected. Open. Nice. So just am I fully. Cool. All right. So let me run. Okay, Docker compose up. So what this is doing is it's doing is fetching my WASM Edge quick.js. So this is that interpreter, really small footprint. I think it's less than a megabyte. So you know, super small. I've got the WASM Edge repo here, and what I'm doing there is they provide the modules, so they don't package that with the binary because it's all JavaScript that's loaded in, right? So you have to kind of take those modules down if you plan on using any standard libraries. But I wanted to pull it in just to give an idea for kind of basic support for most things on the size of the image. And then it's just copying it over and running the runtime. So WASM Edge is the runtime. And then it's running my interpreter as the main binary. And then I'm throwing it the file, just that super simple file. Just like if I were, I could, you know, in a different world, I'd just replace all those first 4 parts of the command with Node. All right, and then let's do. And then my Docker compose, again, very simple, and I'm going to go ahead and proactively change that so it doesn't cause us problems. Okay. Build. See how fast this goes. Oh no, wrong one. That was really fast, but it was wrong. All right, this is what I want to do. Okay, so I'm building this. I meant to do this before, but oh, okay, still cached. Good. All right, cool. I was worried that would be very slow. So we're good. So it's up and running. So now let's go make sure it's working. So same little curl. Hey, hello world. It's different, so we know it is actually working. So that's cool. And hopefully, this is a much smaller footprint, right? That's the goal here, is that we now have created an image with very minimal needs. And that image, just again to reiterate, this is an image provided by WASM Edge, which is really nice of them. So it's as small as they can humanly make it to for just what's necessary for Docker itself, and then for the WASM runtime. So we're going to see what our what the image sizes are and how they compare. So we'll do. All right. So we went from Node Alpine, 54 megabytes, super simple contrived solution, to less than 5 megabytes, 4.26, like tiny. That's amazing, right? Like you can potentially make a fully fledged Node image doing lots of stuff. So quick.js does support anything and everything, most things you can think of for standard objectives, and it could be less than 5 megabytes. That's pretty amazing. So any questions there before I move on to the next one? The next one is going to be showcasing Docker Desktop. Now, I'm not a massive Docker Desktop fan, especially because they started making me pay for it. That was my biggest problem. But they have done a really good job of trying to be at the forefront of engaging with WASM and really adding support that is easy for for almost any developer to kind of get up and running with. So that's why I'm going to show it to you today. So again, how this works is we're just going to tell Docker, hey, use the WASM runtime. I don't want to use the normal containerd runtime. I want to use the WASM Edge containerd runtime, and it's also going to be a different platform for my image, right? So similar to like if you were to build images for ARM, right? It's a different architecture. So same thing with these images. There's a different architecture associated. So that is all you have to do. And then the Docker file itself, very, very simple. It's a scratch, so empty, nothing. And then I'm just going to give it the WASM Edge quick.js, that same small binary, and I'm going to provide all the major modules that are supported or that try and simulate Node.js support. I'm going to add that same file over, and hopefully this all works. And let's see. So yeah, same thing here. One thing I do need to do is change this. We'll do it to 8083, just be a bit different. All right. So close this one off. My other major problem with Docker Desktop is it's pretty slow sometimes when working on the integrated terminal. Okay, so down to this one. Okay, let's just do dark. I think it's all cached. Let's hope. It's not. Literally just I badmouth Docker Desktop and then immediately it starts to badmouth me. Okay, thank you Docker Desktop. I appreciate your willingness to work. Okay, so it is now running, all right, and it's now on localhost 8082 or 8083. Hello world, it works. All right, so now the really interesting part. Now, how big is this image? All right, anyone gather a guess? Anyone gather a guess? All right, shy crowd, here we go. It is less than a megabyte in size. So just those files, all those modules that are in there that provides almost general Node.js support, that's very simple contrived solution. We're very, very minimal footprint. And the goal here is that this will get even smaller as there's more support, as there are better WASM JavaScript runtimes like SpiderMonkey that's meant to provide better performance and also smaller footprint. So this is, again, we're looking at a very immature product here, and it's already solving a really tough problem, which is the footprint of artifacts. Cool. So the next one is one of the platforms that I mentioned earlier. It's called Fermyon, which is a weird name, but like most technology companies, they went with it. It was born out of a Microsoft research company, or a company Microsoft bought and acquired, called Dace Labs. So basically, several of those guys and gals moved over and wanted to create their own platform that handles WASM binding. So the goal here is that they're trying to create as quickly as possible, by adhering to the WASI standard as much as possible, a platform that allows you to build WASM artifacts and deploy them as kind of typical serverless, just APIs and potentially like scheduled jobs and things like that. So that's the overall goal. Again, I think I've said it at least 50 times. We could have played a drinking game. It is experimental. It is non-production. It is beta, alpha, whatever you want to call it. But it's really moving really well, and hopefully they will even do better than Docker Desktop and easily work and quickly work. All right, so I have here I had to do this in a very different, VM. All right, so let's see here. Okay, so, all right. So where this starts is Fermyon. So here's a few notes about Fermyon. So it's built with open source services. So if you're a big fan of HashiCorp stuff, they are like all over it. They use Console, they use Nomad. They also use Traffic, which if we got platform engineers who are big on Kubernetes and probably familiar with that. They created, again in sort of coordination with DSlabs, they've created their own package manager, a bit like a Docker registry, but for WASM binaries called Bindle. And there's a lot, they basically went the extra step further to try and make that in a similar way to reduce the amount of storage as possible, similar to how Docker images work with layers. So they've done that now with in a way with WASM. They've created an integrated development environment, sort of, is still again up and coming, but using Spin, so a pretty simple CLI tool to build, run locally, and then deploy to a specific location. So either to their cloud environment or to a locally hosted or on-prem or in your own cloud. So it's pretty easy to kind of get going and get started. And they got loads of templates on a lot of different languages to make life work. So pretty cool. And one of the things I really love about it is the configuration to sort of deploy and set it up. Doesn't use any YAML, doesn't use any properties files, and doesn't use any JSON. It's great. It uses, I really like this format. It's called TOML. So if you're familiar with that, it's way simpler to read. It's much nicer, in my opinion. So if you're ever having a hatred for Kubernetes YAML files, switching to this will ease that a bit. Okay, cool. So jumping in here, let's look at some of this code. So the actual code here, again, kind of like if you're writing a Lambda, right? There's this particular way you need to expose that handle request, just like with Azure functions as a service or Google's cloud functions. This is their packages that they have. This is their approach. Again, still in the works, but pretty straightforward, pretty simple. And this is doing something that is still contrived, but a little less contrived. It's actually doing something, which is a fetch request. So this is a fetch request to a random API and gives facts about dogs. So hopefully we got some dog lovers in here. And essentially all it's going to do is fetch that request whenever I call this API, and then return it back to me and give foobar headers. So very simple, just sort of a contrived solution, but still semi-useful. All right, so then the next thing that I'm going to do is, I'll show you guys my package JSON. So out of the box, it comes with this build package JSON whenever you're for this particular template. Since I'm using JavaScript. So I'm going to go ahead and do an npm run build. And it's because I'm in the wrong place, so that never helps. I just wish it would like go to the other line now at this point. Npm run build. Alright, so this is going to build my WASM binary, hopefully successful. I'm going to talk about some of the things it's putting out here. So, so essentially if you see there it says pre-initiating using Wiser. Now this is really cool because it's, again, optimizing that and reducing the startup time. So Fermyon is really trying to make, even though the WASM binary is already small, it's already going to be pretty good about starting up quickly. They're going the extra step by using Wiser, which is a package that helps pre-initialize WASM binaries. So basically gets it started up, takes a snapshot, and then lets it, when it goes to get deployed within a WASM runtime, it can jump off even faster. This is a similar approach to if you're familiar with AWS and what they're doing with Java for their Lambdas. So they are now integrating this kind of snapshot approach to initializing the JVM with your jar or your code, and so that way it reduces that startup times for Java. So similar idea, just different technology, right? And it also uses another utility, WASM-op, to help optimize that WASM binary, again, to try and make it as small as possible, because that's the goal of the platform. Okay, so now we've run it. So now if I wanted to actually spin it up locally, it's actually, the command is actually called spin up, which I think is the whole reason that they did this, called it spin, just so they can say that. I think All right, pretty quick. It's going to spin up a local version of this. I can go here. Let's see. Okay, nobody's going to be able to read that. So here we go. What's our fact? Boy Scouts and Girl Scouts can earn badges for dog care and pet care. I hope that was informative for everyone. So yeah, so it's pretty fast. You know, it kind of showed up lightning fast on this local deployment. You know, really a nice little integrated development environment to help you get up and going. More work is being done to kind of make it to where you get like the hot reload and those types of aspects. And what's also nice, especially with this, is that you can just run this, you know, locally with Node.js or you know, whatever your kind of local JavaScript development tooling is before building and deploying, right? So the next step would be deploying to an actual Fermyon instance, right? So I have this locally deployed on another WSL. It was giving me a few troubles earlier today, but hopefully it's gonna play nice for me. So now what I can do is, this is what was not working. So the idea here is that it's as easy as 1, 2, 3 to click spin deploy, and then no. All right, so first I need to load my environment variables, and then hopefully it's as easy as doing spin deploy. How are we on time, by the way? Good?
Yeah, okay, cool.
Awesome. All right, so spin deploy. We'll see if this works. This was not working, but there is other ways of making it bend to our will. It is still not liking life. I don't know why. Sometimes the docs are just wrong. Maybe. I don't know. Okay, so instead of that, what we're going to do is do a spin push. Spin push. Spin build, spin push. Make sure.
What was that you were trying to start up there? Was that like a different... Is it a Fermyon VM itself?
So there is, I have running in another VM here. So if I do PS aux, you'll see a lot of crap in here. Nomad traffic. So this is like the Fermyon, all of a single node instance of Fermyon, sort of like a kubelet or something like that, where I have an entire platform there. So the goal here is that I've built my local image of spin. And now I need to want to push it to that location. And I can actually, let's make sure it's up because, all right, so it is up. I think I should have an app. Okay, I have a user. So I guess I'll quickly run through. This is your very simple dashboard that they provide to look at your apps. So to add, you can click this add, and there are currently no bindles. So it's very simple to deploy. It's just going to take whatever the most recent version is, show you the most recent version of your application here, and then you can create a deployment. Ideally, you should also be able to do it from spin deploy. So let me spin bindle push. That's what it was. Okay. All right. Now we're cooking. This is all coming back to me now. All right. So I'm going to push this binary up. Push to the server at error creating. All right, so I think the demo gods have finally come back to fully chastise me. So unfortunately, I do not get to show you the final bit of this, but I will show you one thing more, again, with Fermyon, or two things more. I was going to show you when it was deployed to its natural habitat, but we'll do it locally here. So again, one of the ideas that Fermyon's trying to lean into is WebAssembly, that it's super tiny and also super secure. So anytime that it needs to request something outside of that binary, it's basically going to require you to opt in to that. So for instance, I'm hitting an API here. I'm saying, hey, my WASM binary is allowed to access this particular host. if I were to take this out, all right, then I will get an error. So now I need to do another npm run build. All right, and then we'll do npm run. All right, so then if I go back to here, whoa, there it goes. You can see the log there. So if I uncaught internal error, destination not allowed. So again, you know, this is amazing for platform engineers if you're or SecOps, right? You know, you can clearly see everything that binary is allowed to reach out to and connect to. So kind of upfront, out of the box, it's providing that kind of security that you can hope for in a really integrated platform. Unfortunately, it's just not working for me to deploy to it. So that is, I'll blame the trains being canceled because I was going to take the train here and do a little bit more prep, but unfortunately they canceled my train and I had to drive, so there you go. And then the last thing I want to show you is, you know, all of the stuff here is, so I gotta find the IP now that it wants to use. So all the stuff that run that platform, you have access to as a single node. And again, they provide templates, I believe it's Terraform, for infrastructure as code to deploy this multi-node instances of this to GCP, AWS, and I would hope it operates more efficiently and better than for me in my local node. So let's go here. Okay. So like for instance, the Notepad, I can clearly see that everything that I want to be up is up. You know, got my Hippo, got my Bindle. Hippo's the web client there. Bindle's that package manager, and Traffic is the thing moving stuff around. So when stuff gets deployed, you'll see jobs there as well, because Notepad is what's doing that orchestration or task scheduling. And then you have direct access to console as well. And then you do have access to Traffic if you needed to do anything kind of specific with that. So again, it's a platform that you can do anything with. It's open source, so hopefully a lot of the tooling is familiar, and that's kind of the goal of Fermyon, is provide some familiarity, but do it in a nicer, newer way, or newer approach. And that's really all I had for demos. Apologies on the last one, not fully living up to expectations, but that is everything that I have. Do you guys have any questions? Anything? Yes?
Do you know what the performance is like versus something like V8 when you were building a compiled version of running JavaScript? Do you know what the performance is like versus something like V8?
Okay, so for QuickJS, for small like things like that or simple stuff, it's pretty, it's like negligible.
Yeah.
But as soon as you get to bigger Express apps, you'll start to see, and that's kind of not what QuickJS was meant for.
Right.
It's really meant for super small amounts of code. But if you were to kind of have a lot going on with your Node.js, it's going to not look as good as in terms of performance.
Yeah.
But with SpiderMonkey, they've started to, like, for actual kind of reasonable workloads, comparing Node.js or Dino to it. It's actually looking anywhere from like 8 to, I've seen all the way up to 13 times of kind of increased speed and efficiency and throughput. So incredible performance increases there, theoretical performance increases because obviously it's not production ready, but so I imagine that number will be coming down as it matures, but still very interesting nonetheless. It is going to provide a nice way to kind of do JavaScript. And one of the ideas with WebAssembly for the backing for JavaScript, which seemed a bit weird at first, right? Because WebAssembly was meant to complement JavaScript, but is to be able to run JavaScript in sandbox environments within JavaScript. Sometimes you want that level of kind of security or walled nature between maybe some of your active processes. So that would give you that capacity.
Cool.
Yes?
As this matures, do you think there will be quite a large shift to more WASM sort of stuff rather than just HTML, CSS, and JavaScript as alone? Or it'll be people will go for those smaller, images, sizes, the performance, etc.
I think if the more, like just with containers, right? That was kind of people were aware of containers for a really long time, but it took a while for a lot of companies and organizations to kind of switch into actually using those in production, and that was because of the barrier to entry, right? Like lots of technical problems came with working with containers, and it really wasn't until you had robust orchestrators that you could rely on that really enabled that, or robust cloud services that makes that super easy. So I think the same thing is going to be the case with WASM. The caveat here is that there's more community support required with WASM. So to me, the only way it's really going to live up to the hype and truly become this next wave of cloud compute is if every different project that is working for their language towards support truly achieves that near 100% support of what was previously available. So I hope I think it really solves a lot of problems that are really pertinent today. In terms of providing more efficiency, more performance, with hopefully without the technical challenges involved. So that's the goal, and I think if the community can continue to thrive and push forward, I do think it will happen eventually. I think it might take longer than containerization, though. That's my only kind of major fear, just because you got to rebuild compilers, like that takes a long time, and then you got to get people on board with using it, and then libraries will probably change as well, and there's a lot of legacy code that won't work. So a lot of things that they're going to have to jump through. I do think once it becomes mature enough, newer applications, just like we saw an advent in serverless, like people going straight into serverless, not really worrying about kind of creating large microservice architecture or anything. So startups and things like that. I think you will see them starting to use WASM in the future because you're all writing net new code, and there should hopefully be pretty good support. So that's my general prediction. I hope, but there are a bunch of bumps in the road that kind of actually get us there.
Where would you put this on your tech radar? Adopt, assess, or trial?
I would say, I think if you're a front-end developer, especially if you like .NET, I know I saw a few people who had .NET backgrounds. Blazor is really cool from a front-end perspective. WebAssembly, there's several other popular frameworks for WebAssembly on the front end. And I think that's always going to kind of grow and become really useful, especially for really rich interfaces. So I think that's happening. That's pretty mature. In terms of the backend, I'm hoping by end of 2023. I'm hoping by the end of next year that we start seeing companies actually using it in production on a wider scale. That would be my hope. That we've basically, a lot of it is going to hinge on how quickly those WASI standards get created. So they are supposed to be, the two most important ones are multi-threading, because all WebAssembly is not currently single-threaded. So multi-threading is going to add in a lot of support for those for other languages, and then garbage collection as well. So out of the box garbage collection. So once those are solidified this year, hopefully it'll give everybody, all these communities, another year to truly invest in support for the runtimes. Cool. Any other questions? Any questions from online, or chat, or anything?
No questions online? No?
Awesome.
All good. Thank you very much.
I appreciate it, guys. Thank you.